Okay, hi everybody, and welcome back to TezAsia Hackathon to 2022. I would like to introduce you a crowd. Uh, so without further ado, crowd, I would like you to take the stage. Yeah, thank you.
Okay, so hello everybody. So my name is Claude. I work as a developer relations for ECAD Labs. So it's a company that's mostly known in the Tezos ecosystem for developing Taquito. Today I'm going to talk to you about LIGO. So we're going to have an introduction about the LIGO language. I'm going to show you how it works, what you can do with it. We're going to write a simple smart contract in order to demonstrate how the syntax of the language works and what you can do with it. First, I would like to introduce a little bit LIGO. Because I work for Taquito, I do a lot of app development and I work a lot with JavaScript, but I've been using LIGO for 2 years and a half now. So I have a lot of experience with the language, and I also write contracts within ECAD Labs to test different features of Taquito. I use LIGO a lot. I don't know exactly what you know about LIGO. So first, LIGO is a programming language that is used to write smart contracts on Tezos. It's a high-level language that you can use for the smart contract, and that's going to compile to Michelson to put the code on the blockchain. It's one of the three languages that most of the developers on Tezos use at the moment. There's LIGO, there's SmartPy, and there's Archetype. So those are like the three languages that you will probably see to develop contracts on Tezos. One of the main difference between LIGO and SmartPy, for example, is that LIGO is a language. So it's a language that was especially designed for Tezos. So it's not a library for another language. So LIGO, you use LIGO just to do that, to develop smart contracts. One of the features of LIGO is that you have different syntaxes for the language. So you can use the syntax that makes you more comfortable if you have a prior knowledge of the language that the syntax is based on. For the rest of this presentation, I'm going to use LIGO and Camel LIGO interchangeably. Sorry. I'm going to, when I use LIGO, I'm going to mean Camel LIGO. So Camel LIGO is one of the syntaxes of LIGO that is based on the OCaml language. So the syntax is very close to OCaml. You also have Pascal LIGO, where the syntax is closer to the Pascal language. Recently, they added a new syntax that's called JS LIGO, where the syntax is closer to TypeScript. And there's another syntax, ReLIGO, that's based on ReasonML. Those are like the four syntaxes that you can see when you read smart contracts written in LIGO. But here I'm going to show you how to use Camel LIGO. There are some perks of using Camel LIGO. There are some benefits, some things that I like better when I use Camel LIGO. For example, you're going to find a lot of examples online. There are a lot of contracts that were already written in Camel LIGO, and when you start as a developer for smart contracts, it's always very interesting to check contracts that were already written by more experienced developers. So you can see how they structure the contract and how they use the language. The second benefit that I like about Camel LIGO is that it's a functional language. So there are a lot of functional patterns that you can use and that make the language safer, but also more readable and easier to reason about. Also, maybe the third benefit that you can have about using Camel LIGO is that the syntax is very close to OCaml. So even if you're not an OCaml developer, you're going to be familiar with the syntax of OCaml. And when you work in the Tezos ecosystem, that can be an advantage for you, because you will be able to read OCaml code. So you won't probably be able to write it, but you will be able to read it, because the syntax is going to be very similar, and because the source code of Tezos is written in OCaml. So you will have an advantage by knowing Camel LIGO, and you will be able to read some OCaml code after that. All the contract code is going to be written in a file. So that file is going to have a specific extension. So for Camel LIGO, it's going to be .mligo, and you have different extension to tell the LIGO compiler to use which syntax you're going to use. So right now I'm going to share my screen, and we're going to do some live coding. I'm going to show you how, so I'm going to write a very simple contract to show you how Camel LIGO works. And at the same time, I'm going to explain to you the syntax and all the different things about Camel LIGO. So just give me a second. Okay, here. Okay. So here, I think it should be working.
Yeah. Okay. Screen share works.
Okay.
Yeah.
Yeah. Okay, great. So okay, so here you see I already have some files. So I already worked on the contract. I'm going to use it for a reference, just in case something doesn't work, which it generally happens. We're going to create a new contract here. So we're going to create a lottery contract. So it's a very simple contract where the players are going to be able to buy a ticket, and then when all the tickets have been bought, we're going to end the game, and we're going to use a very simple function to determine who is the winner. Okay, so the first thing that you want to do is to create that .mligo file. So in general, when you have a more complex contract, you're going to divide the different parts in different files, and LIGO allows you to do that and to include the different files in the main file. Here we don't really need to do that because it's going to be a very simple contract. So we're going to write everything in the same contract. So the first thing that you need to know about the structure of a contract in LIGO is that it's going to follow more or less the structure of a Michelson contract. So in Michelson contract, you have 3 parts. You have one part for the parameter type, you have one part for the storage type, and then you have one part with the code, with the logic of the contract. So in LIGO, it's going to be the same. You will have to decide the type of the parameter, the type of the storage, and then you can start writing your code and all the entry points and the behavior of the contract. So let's start with the storage, because the storage in general is going to include some simple types that I would like to show you. When you want to write a new type, you're going to start with type and then storage. And here, so for the storage, we need 4 properties in the storage. We need to keep track of the players. So every time a player buys a ticket, we need to register the player in the contract. We also need to know how much the ticket is going to cost. So we're going to keep track of that in the contract. We also need to know how many tickets are available. So we want to have a threshold of the number of tickets that players can buy. So we're going to keep track of that in the storage too. And to finish, we also need to set a maximum number of tickets. So when we reset the game, the contract knows how many tickets should be available for the next game. All these properties are going to be in a type that in LIGO we call a record. So if you're familiar with the JavaScript, a record is like an object. So it's going to have different properties, and these properties have different values, and these values can be of different type. So you can group different values together in a record. We're going to start with so for example, the maximum number of tickets that we want to have. So you write the property like that as a string, and then you put a colon, and you tell you set the type for the number of tickets. So here it's going to be a NAT. If you're not familiar with that, in LIGO, you're going to have two different types of numbers. There's going to be one number that's is going to be a NAT. So a NAT is a positive number, and then you have int that can be a negative or a positive number. After that, we have also the cost for the ticket cost. So this one is going to be of type Tez. So Tez is a type to represent what represent Tez in the contract. After the ticket cost, we need to know how many tickets are available. So tickets available. So we're also going to track the number of tickets that are still available using a NAT number, and we're going to decrement that number every time that a player is playing and buying a ticket. I want you here to see that I'm not setting the value. I'm just telling the type that I'm expecting. So here I'm not going to think about the values, because the values are going to come when you call the contract. Here you just set the type, and you just tell the contract, okay, the storage must be of that type. And to finish, I want to show you a map. A map is a list, is a collection of entries with a key and a value. So the key can be mostly of any type. There are some types that you cannot put as a key, but in general, you're going to use keys of type NAT or string, or maybe another record, and then a value that can be also of another type. So all the keys in the map must be of the same type, and all the values must be of the same type, but the keys and the values don't have to be of the same type. So you can choose to have a key that's a string and to have a value that's a NAT. So all the keys are going to be string, and all the values are going to be NAT. So here, for example, we want to keep track of the players, and so to declare the type of the map, you open some parentheses like that, and then for the key, so for the key, it's going to be a NAT number, and for the value, we're going to track the address of the player. So it's also a type in LIGO that you can use that represents an address. So it can be an address of an implicit account or the address of a contract. And then after that, we put so it's a map. So we put the keyword map for this type. So now here we have the storage for the contract with 4 properties that we're going to use in the contract for different things that I'm going to show you when we start writing the logic of the contract. So after writing the storage type of the contract, we can now write the parameter type. So here, so let's call it param. So the parameter type of the contract is going to be a little bit special. It's a type that we call a variant. So if you haven't done functional programming before, maybe you're not familiar with that kind of type. Maybe if you know some TypeScript, maybe you're familiar with enums. So a variant is going to be an enum on steroids. You're going to be able to do much more with a variant that you can do with an enum, but the concept is very similar. and that variant is going to emulate the entry points of your contract. So I'm going to show you right now. So here in the contract, we want to have 2 entry points. There's going to be an entry point to buy tickets. So a player is going to call that entry point to buy a ticket. And then there's going to be an entry point to end the game. So a player or a third party is going to call the contract to end the current game and to distribute the winning to the winner. So we're going to have 2 entry points, and we use a variant to represent those entry points. And so you just write it like that with the vertical bar. And the first entry point is going to be buy ticket. And the second entry point is going to be end game. And so those, the LIGO compiler is going to take those names and put it in lowercase and use them as the entry point annotation in Michelson. So here, when I write buy ticket and end game, you know that your entry points once in Michelson are going to be named exactly in the same way, just that they're going to be in lowercase. And here you can see that I don't need to put any parentheses or a semicolon or anything. That's how you write a variant in LIGO. Just that vertical bar and then the name of the branch of the variant. And when I was saying that the variant is more like an enum on steroids, because in TypeScript, when you have an enum, you just have like different branches like that. But in LIGO, you can also attach a value to each branch of the variant. For example, so it's not relevant for this contract, but I just want to show you quickly. In general, the example that we give is an enum of type color, where you have, for example, red, let's say blue, and green. Okay, so here it looks like an enum, but for example, green, I can attach a value of type nat. So here I'm going to have the value green, but I will also have a number that's attached to that value. And then later I can also use that value when I use the variant. And here, as a value for the branch of the variant, you can use a lot of different types. So you can use a nat, or you can use a string, but you can also use a record like we just made for the storage. So there are a lot of values that you can use. So it's very interesting when you create a contract to use that kind of pattern. Okay, so now we have the parameter type and the storage type for the contract. The third thing that we need to do now is to create the code for the logic and the behavior of the contract. So in LIGO, it's going to be a function. That function is going to be called main. By default, it's called main. You can give it another name, but you will have to tell the compiler that that function has another name. If you call it main, the compiler is going to figure out that this is the main function, and so you don't have to explicitly set it. The way to create a function in LIGO is going to be like that. So you use the let keyword. So the let keyword is to declare a new variable, and then you have the name of that variable. So that the function is going to work the same. And then after that, when the contract is called, the value for the parameter and the value for the storage are going to be passed to the contract. So we open some parentheses here, and one thing that you have to know about the function here, so I'm using some parentheses, but they are different from the parentheses that you would use in JavaScript, for example, where they are required. Here, the parentheses are more like to help the compiler follow a certain order of execution. So here, I just want to tell the compiler first, you have to look at what's inside the parentheses, and that's going to be the argument for the function. So the arguments of function in LIGO, like in OCaml, don't need parentheses. So here we're going to get the storage, the parameter, sorry, and the storage. So it's going to be a tuple. So let me just write like that so you can see how it looks like. Okay, so tuple is just a type. So it's going to be a little bit like a record, but you don't have any names for the properties. So in general, it's very practical when you just want to pass some values like that, and you don't really want to give them a name or something. And here you can have some, you can destruct the tuple, and so you can name each field of the tuple. So here in the function, the parameter value is going to be p, and the storage value is going to be s. So here that's going to be the argument for the main function, and then you also have to type the return value of that function. And just like in Michelson, the main function is going to return a list of operation and the new storage. So in general, because that's something that you're going to reuse in your contract, you would like to create a special type for that that we're going to call return. And so it's going to be a list of operation. And so you see it's a tuple. So I use the star like that to separate the different fields of the tuple, and here storage. And then we can use that return like that. So now I know that the main function is going to take a value, a tuple with, on the left, you have a value of type parameter, and on the right, you have a value of type storage. And it's going to return another tuple with the list of operation and the storage. And then something that's also very simple when you use Camel LIGO is that when you want to start writing your function, there's no curly braces, there's nothing. You just write the equal sign, and then you indent it, and you just start writing your code for the main function. Okay, so now we're going to have to know to make the difference between the two entry points that we have. So we're going to use probably one of my favorite features of functional programming. That's going to be pattern matching. So pattern matching is going to take a variant, and then according to the value of that variant, you're going to be able to set different behaviors. And we're going to use that to redirect the execution of the code to one of the two entry points. I will write it, and I will explain you at the same time what it does. So when you want, here we're going to pattern match on the value of type param. So we're going to use it here. So you just put those two keywords between the variant that you want to pattern match. So match the value and width, and then just like the variant that we wrote before, so we're going to have a first case where it's going to be buy ticket, and then the second case where it's going to be end game. Okay, so because the value of type param can be either buy ticket or end game, so here the pattern matching is going to check that value, and then according to the value of the variant, we're going to have different behaviors. And then that's it. No, that's how you write the entry points for your contract in LIGO. And then, so in general, if you have a simple contract here, you can start writing your code. It's not a problem. But in general, you would like to use a function, so you can keep your code cleaner, and it's also going to be easier to reason about the code. So here, for example, we're going to have one function. So convention is generally to call the function with the same name like the entry point, but it's not required. You can call the function the way you like. So we're going to create another function that's called buy ticket, and it needs a parameter. We're going to pass the storage, and here we're going to have another function that's called end game, and we're also going to pass the storage. So it's also important that when you do pattern matching, that every branch of the pattern matching, so that's a branch and that's another branch, those two branches must return the same type of value. Otherwise, you're going to have an error. So here, our two functions have to return a value of type return. So on a list of operations and the new storage. Once again, you will see that the value that's going to be, for example, when buy ticket is called, the value that's returned here is going to be propagated, and it's also going to be the value returned by match. And so no semicolon, no curly braces, nothing. You just put it like that, and then we're going to start writing our functions for each entry point. So we have one to buy a ticket, like that. So you just follow the same syntax for a function, like we just saw for the main function. So here once again, put some parentheses, but just because we have to type explicitly the value that we're going to pass to the function. So here that value is going to be the current storage of the contract. And as I just explained, we have to to return a value of type return. In general, what I do, but it's just a personal choice, is that I just do like that. So I return an empty list and the storage, and then I write this one too. And then I'm going to compile it just to make sure that there's no problem with the typing of the storage, the parameter, before I start writing the function, so I can pinpoint more easily where there is a problem before I write too much code. That, and I should have. Okay. Okay, so here you can use the. So LIGO, I will let you check the documentation for that, but LIGO is also distributed in a Docker image. So that's what I'm using here. And so LIGO is the compiler is in the background, and I can just write some commands to compile the contract and make sure that everything is fine. So in general, when you see the Michelson code like that, it means everything is okay. There's no problem, and you can continue. If there's an error, something is wrong, then you're going to have a message that's going to explain to you where the problem is. So now we can start writing the buy ticket entry point.
Okay. Before we start, I guess some of the questions would be, is there an online IDE where we actually can code along with you?
Yes, there's an ID. So if you go to, I think the address is ide.ligolang.org. You can go there and you can code along, and yeah, there everything is already set up. You just have to press a button to compile the contract. You will have to choose the common LIGO syntax. So the IDE lets you choose different syntaxes, but if you want to follow with this tutorial, you have to choose the common LIGO one, or it's not going to work.
Okay, and the next question will be: is there any prerequisite before you actually learn LIGO?
Sorry, it cut. I didn't hear the question.
Sorry. So another question will be: is there any prerequisite to learning the LIGO language?
Mm-hmm. Yeah. No, there's not prerequisite. No, you. Well, if you know some OCaml, of course, it's going to help you to understand the syntax. So as I said in the beginning, that there's going when you learn Camel LIGO, especially, there's going to be a small learning curve because you have to get familiar with the syntax, and the OCaml syntax is a little bit different. But very quickly, the syntax is starting to make sense. And actually, I was like that too. I started with LIGO first. And then I switched to Camel LIGO because all the contracts that I was working with were written in Camel LIGO. So at the beginning, it was a little bit strange. And actually now I really enjoy it. No, I really enjoy the functional patterns in the language. So yeah, maybe at the beginning you have to get familiar with the language, but then it starts to feel natural very quickly, and you can write the language. You're already familiar with the syntax, and there's no problem.
Okay, yeah, I think you can continue. That's the last of the question. Thank you.
Okay. So okay, so now we're going to start writing the buy ticket entry point. So in general, what you want to do when you write the code for an entry point, first you want to do some checks. There are some the storage must be in a certain state. There are some conditions that must be fulfilled before you execute the code of the entry point. So that's what we're going to do first. We're going to do that just to make sure that everything is fine before letting a player buy a ticket. So here again, so I'm going to tell you when it's a personal preference or when it's something from the syntax. Here it's more of a personal preference. There was a change that was introduced in LIGO recently, where if you want to access different values from the context of the execution, for example, the address of the sender of the transaction, or the balance of the contract, or the amount that was attached with the transaction. Before there was just a property on a module that you can use, but now it's a function, and it can become a little bit tedious to use that function multiple times in the body of the main of the entry point function. So in general, what I do here is that, for example, I know that I'm going to need the address of the sender to check it later. I'm going to save it in a variable so I can use it later, and it's also going to be more readable. So when you use LIGO, you have different modules that are going to be available out of the box for you to use, with different functions, different methods, different properties related to the execution of the contract. One of the main modules that you're going to use in LIGO is called Tezos. And for example, with this module, we're going to call this method that's called getSender, that's going to return the address of the sender of the transaction. And one thing that you must know about functions in Camel LIGO, but it's the same in OCaml, is that you cannot call a function without an argument. So when you don't have any argument to pass, you use the unit. So unit is a special value that's more or less like undefined in Java. It's not exactly the same, but you can see it as undefined. So it's a value that has no value. So here we in Camel LIGO, you're going to represent it like that, with two parentheses and nothing in between. And then also, so one of the things that's a little bit strange at the beginning with the OCaml syntax is, I mean, that was strange for me, so I imagine it must be strange for other people, is that in keyword. So as a shortcut, you can see the in keyword as a semicolon. It's not exactly the same, and later I'm going to show you an example about something you can do with that in keyword in Camel LIGO. But in most cases, and at the beginning, you can see it like a semicolon to say, okay, that's the end of the expression, and now I continue my code with something else. Okay, so here we're saving the address of the sender. We're also going to use the amount that was sent along with the transaction, because we need to make sure that the player sent enough Tez. And here the same, you use the Tezos module. And there's a get amount function that takes no parameter. So we put the unit here, and like that. Okay, so now we have that set up, and we can start checking that everything in all the parameters and the state of the contract is correct. So first, you don't want players to buy tickets if there are no more tickets available, because as you remember, we're going to track the number of tickets that are available. So first, you want to make sure that there are enough tickets available before a player tries to buy one. So here we're going to see how conditions work in Camel LIGO. And spoiler alert, they work like in OCaml. So if you know some OCaml, it's going to look very familiar. And so like in a lot of other languages that you may be familiar with, conditions are going to use those keywords if and else. There's going to be a little difference here. So we write if, and then we want to make sure that, so here we have the storage. So the number of tickets available is a property of the storage. And here, so we want to make sure, if there are no more tickets available. So if that number is equal to 0n, so 0. So that's also something about common LIGO. So if I write 0 like that, it's not going to compile because 0 is an int, and here I want a value of type nat here. So you're going to represent it differently just by putting an n at the end. So now it's fine. So I want to check if there are no more tickets available. I'm going to make the contract fail. So a contract failing means that the execution of the contract is going to stop, and all the changes that were made in the storage at that point are going to be reversed, and the contract is just going to keep the storage that it had before the transaction. So as soon as the contract fails, there is no change in the storage. That's why you have to be careful if you want if there's something, some condition that you want to check, but at the same time you want to change some properties of the storage. You cannot make it fail, or nothing is going to change. So you have to find another way to do it. When the contract fails, there's no change in the storage. So here in common LIGO, you will have that then keyword to introduce the first branch of the condition. So it's a little bit in like like a ternary condition in JavaScript, where then is going to be the interrogation mark, and else is going to be a column. So here, okay, here we have to make it fail. So we use that keyword fail with. That's going to make the contract fail. And then you can also you have to set some value. So in general, I set a string, but I know other developers that use a number. At the moment in LIGO, you can only make the contract fail with a string or a number. So here it's perfect for this use case, and it's very available. So now when the contract is going to fail and you have an app, and for example, you use Takedo, then Takedo is going to receive that this string here, no tickets available. And then from your front end, you can have different behaviors according to the kind of error message that you get from the contract, and you can update your front end according to the error that happened at the contract level. Next, after checking if there are tickets available, we're going to check if the amount that was sent by the player is correct. So here we're going to write else if. So you can also, like in other languages, you can have if else, or you can have if else if, else if, and else at the end. So the same like with the variance, it's important that the values that are returned by each branch of the condition have the same type, or it's not going to compile. So you cannot have something that's a branch of a condition that returns a string and the other one is going to return a nat. So it's not going to work. You have to use the same type. And here, the LIGO compiler is going to figure out what type it is by the other branches. So here we're going to make it fail again. So we're going to check if the amount is less than the ticket cost. So in general, you would like to check if the amount is exactly the ticket cost. But here I want to show you how to forge an operation at the end of the entry point execution. So we're going to put it like that just for demonstration purposes. So okay, here if it fails, then again you write then, and then we're going to put a string here, invalid amount, for example. And now we check that the parameters of the execution of the contract are correct. We write else, so we can continue the code. In general, you indent it like that, and then you continue. So you see no curly braces or nothing like that. You just continue your code like that. Once you check that everything is correct. Okay, so the first thing that we're going to do is to update the players map. So we want to put a new player in the map to track how many players are playing. So we're going to call it new map. So the same again with the let keyword equal. And then, as I told you, there are a bunch of modules in LIGO that you can use with methods to help you. So we have a map module that you're going to use to add a new value in a map. So it works like that. You call the method on the module, and then you put first you will put the key that you want to use for the map. So here for the key, we're just going to use the size of the map. So the size of the map is going to increment every time we add a new player. So when the next player comes and buys a ticket, the number, the size of the map is going to be different. So every time it's going to be a different number. So here again, we use the map module that has a size method where you just pass the map like that. So it's going to return a nat number. So it's exactly the type that we expect for the key of the map. And here again, you see the parentheses. So the parents here are more used in a mathematical way, just to for the order of execution. So first, I want to get that nat number. So I tell the compiler first get me that nat number that you get with the map.size. And then after that, I can use that number as a key. And so here we have the key. Now we have the value that we want to add to the map. And we're going to use, oh no, I called it sender. So sorry. The sender like that. And then the map that you want to update. And then that in keyword. No? So now it's over. So that's the map module, and that's how you add a new element, a new entry to a map. Let's call it new players, just to follow. The first one was player. This one is new players. Okay, now we're also going to decrement the amount of tickets available. So the next player, so there's one ticket less for the next player to buy. So let's call it new tickets. And so here I'm going to show you something very important to remember when you write LIGO code. So the amount of tickets is available is in that property in the storage. And so we're going to decrement it. So -1. And so what's happening is that actually it's not from LIGO, it's from Michelson. When you subtract two nat numbers in Michelson and also in LIGO, you're going to be given an int number. And here you see it's not going to work because we want to have a nat number for the new number of tickets. So you have a little function here. So once again, we put parens, just to say, okay, that's you do that first, and then when we get that int, we use there's a little function like that you can use that's called abs. So for the absolute value of the number, and then here we're going to get a nat back. So now we can update the storage with that value. So before we had an int, and we cannot put an int where the contract is going to expect a nat. So we use abs to make it a nat. Okay, so now it's the part where I'm going to show you how to how to forge an operation and send it at the end of the execution of the entry point. So this one, yeah, there's a lot of very new syntax that you have to learn, but you will see it's very logical what happens. So we're going to use amount. Take a variable like that, amount to return. That's going to be the amount in Tez that we have to return. So since the last upgrade on Tezos, when before you were able to subtract two values of type Tez, and you would get a value of type Tez back. Now, for some security reasons, it's not possible, and you return you get an option. So an option is a special type of variant, like the param here. I'm going to show you how it works. So we're going to match so the amount that the user sent. I think the parents are necessary here, but okay, let's try like that. So the amount that the user sent minus s dot ticket cost. So sorry. So right now, so we know that the amount that's sent cannot be greater than the cost for a ticket. So it's either going to be the same amount that was sent or a greater amount. So now, because we have two values of type Tez, we're going to get a variant, an option variant back, and an option variant works like that. So we have two branches, a non-branch and some branch, with here like the result of the subtraction. So if it's none, it means that there was a problem, that it didn't work. So we want the contract to fail. So just like before, we write fail with, and then yeah, let's write like in general, it means that there was a muted overflow. So we can write an error code like that. And if everything worked, then we just return the result of the subtraction, and we don't forget in. So here in amount to return, we're going to have the amount in Tez. So if the player sent more Tez, the difference is going to be here, and then we're going to send that difference back to the user. So I'm going to show you how to forge an operation here with LIGO. And here you're going to see some of the beauty of functional programming. Maybe some things that you are not very used to, and after you start using them, maybe you're going to be like me and you're going to wish that the language you use them too. So here I want to have a list of operation. So I'm going to call it ops. And I told you that each branch of a condition has to return the same type of value because they're all expressions. So a condition is an expression that's going to return some value. So here you can use if directly after the equal sign. So that's something that you cannot do, like, for example, in JavaScript. But in OCaml and Caml LIGO, it's valid syntax, and it's a very powerful feature. So first, we want to check that if the amount to return is equal to 0 Tez. Yeah. So if have the same code. So if it's greater to 0 Tez. So here it's the same. Right? You remember I told you here, if you just put 0, it's an int. You have to put an n to say it's a nat, and here's the same. You have to put Tez after the number to say that it's a value in Tez. So if it's greater than that, then we're going to do something. And if it's not, it means that it's 0 Tez. And here we don't have to forge an operation. We don't have anything to return. So we just return an empty list of operation. And here in this branch, we have to return also a list of operation. And then, so now we're going to forge the operation. So we need first a value of type contract. So it's a value that reference a contract or an implicit account on chain. And try to keep it a little bit clear like that. So here too, we're going to use pattern matching because it's possible that the address that we're going to use doesn't exist or something. So there are a lot of safeguards like that in LIGO. And so we have to use pattern matching and start like that. So once again, we use the Tezos module, get contract opt. So here it's a method that's going to turn an address into, a value of type address into a value of type contract. So we're going to use that the sender here, and then with. And here you have to explicitly type the values. So we have to tell the compiler what kind of values we have here. So we're going to use some parens. So actually two sets like that. The first set. Just a second. The first. Okay, yeah. So here we're expecting a value. So here, get contract opt is going to return an option like this one, the same kind of variant of type contract, and then contract has as an argument. And here, because we send the transaction to an implicit account, to the sender of the current transaction, there's no parameters, so it's just unit. Well, if you send a transaction to a contract entry point, then here you're going to put the type of the parameter. So this one here. So here we send like that. So if it's none, it's the same. It means that there's a problem. In general, it means that the contract didn't find the address that you referenced. So we're going to make it fair with 2. Sender. Then some sender. So here, just to explain you quickly, I'm using sender again, but I'm in a different scope. I'm in the scope of the match here. So it's not going to overwrite this one. It's just going to be used here in this scope. So I can use it and then, so it's not those two variables. They have the same name, but they are in different scopes. So they're not, this one is not going to overwrite this one. So in different scopes, you can use the same variable with the same name, but I can also use it. I can call it sender like that. It's the same. And then here, you're going to see that after the in, I'm going to create the list of operation directly. So this one is a list. It's an empty list. And for the operation, I'm also using the Tezos module transaction. So there's a transaction method to create a new transaction. And here, so I don't have any parameter here. So the first argument is the parameter to the transaction, but there's no parameter. Here I'm going to want to return, and here I'm going to use this one here, sender contract. So here you see I sort of pipe this variable inside this function just after the in keyword. And that's it. So this one, let's check if it works. Okay, so of course it doesn't work. Oh no, I'm not. No, it's not it. Sorry, I didn't. So now I have to return, of course, this one here, the list of operation and the storage. So here, so I'm going to return ops here, and then that's how you update. That's how you update a record in LIGO. So you open like that. The record that I want to update is the storage, and then after the with keyword, I tell LIGO which properties of the storage I want to update. So here players, I want to update, and I want to put new players. So Just note that when I update the record or when I set the property of a record, I use equal, but when I type it, I use a colon. Okay, that's a very important distinction to make. And then also tickets available with new tickets. Okay, now should be good. No, we're not good. Oh yeah, here. I forgot in. Okay, and now we have the Mikkelsen. So this entry point is done, and it's working, and it compiles properly. I don't know if there are some questions so far. I will try. I will go to the next entry point. It's going to be fairly easy and reuse different patterns that we already saw. No, okay. So let's go to this one. So now we want to have an entry point to end the game. You know? So either a player is going to end the game, or a third party can end the game. And so you will see that the function that we write to define the winner is going to be very simple. So it's probably not something you're going to use in production, but it's just for demonstration purposes. So you can understand how it works and have a better idea about the syntax. Okay, so here again we want to do some checks. So first we want to check you can only end the game when you still have when you don't have tickets available anymore. So when the amount of tickets is equal to 0. So first, awesome. So that's the symbol that you use to say it not equal. You know, like instead of something like that maybe you're familiar with in common LIGO, it's going to be this symbol, but it means not equal. So if the amount of tickets available is not equal to 0, it means there are still tickets. So we're going to make the contract fail at this point. Game at the end. Okay. And if so, now we know that the number of tickets is 0. So then we can continue and process with the execution of this entry point. So first, we're going to pick a winner. So yeah, we're going to use something very simple to find. So you remember here in the map, every time there's a player, we have a NAT number as a key. So we're going to generate pseudo-random NAT number in the range of the size of the map in order to find an ID for the winner. So we're going to use. So here you can also get a timestamp using Tezos, the Tezos module, and the get now method on it. So here I'm getting a timestamp. Then I'm going to subtract it to get a value of type NAT. So I'm going to subtract it with another timestamp. So in order, there's some casting like that you can do in LIGO. For example, here the timestamp. So I don't want to change the timestamp. I just want to have that value, that numeric value of type timestamp. I want it in NAT. So I'm just going to use 0. The problem is that 0 here is an int, and the compiler is going to complain about it. So you can cast it into a timestamp by just putting the type after it. And that's a pattern that you can use in LIGO also. For example, if you get an address, when you have an address like that, or TZ1 something, blah blah. So here for LIGO, it's a string, you know. So but you know it's an address, so you just cast it like that, and then now the compiler is going to understand that it's an address. So we do exactly the same thing for the timestamp here. We cast a 0 into a timestamp, And then now here we have a value of type nat. So we're going to use some parentheses to continue, and then we're just going to get the modulus of that value when we divide it by the amount of not tickets available, sorry, but the max tickets. So that's the maximum number of players that we can have in the map. So here it's going to generate a nat number that we're going to use. So you see that it's pseudo random. It's not really random. That's why you shouldn't use that in production. And now we can use that that number to get the address of the winner. So once again, we're going to use pattern matching in the map to find the address. So when you want to find a value in a map in LIGO, use pattern matching because it's possible that the key that you have doesn't exist in the map. So LIGO is going to tell you that the key doesn't exist. So we can call it winner address equals and then match. So it's going to be on the map module. There's a method that's called find opt. So in general, the methods, that you can see if they have that opt word at the end, they're going to return a variant of an option variant. So find opt, and here we just give it the key that we're looking for in the map, this one, and which map, and the map is players, like that. And actually the parents are not necessary here. No. But, okay, and just in the other cases, none is going to fail. Get the winner. Maybe there's a problem and we didn't generate the right number or something happened. So here we're going to make the contract fail. And then some. So here now we here in that variable w. So that's why I was telling you about variants. It's very interesting because you can attach a value to a branch of a variant. And here, so we have a variant that's a special variant. It's an optional variant, and you can see here that branch sum has a value attached to it. And in this case, it's going to be the address that we found in the map. And then we can just return it. And that's it. So here, now in the winner address, we have the address of a winner. And now, so now we have to forge a transaction to send it, the winnings to the winner. And here again, you're going to see a pattern from functional programming that's really powerful and that makes also the code more readable and easier to understand and also to think about it. So here we're going to create an operation, and now when I create that variable after the equal sign, I have like a mini scope, and in that mini scope I can declare variables and I can do different things without opening curly braces or anything. The compiler is going to understand what I'm doing. So here for the operation, first, as you remember before, I have to generate a value of type contract. So I'm going to call it winner contract, and so match Tezos get contract of, just like we just did above. So the address is this one. So we're going to have to type it. So once again, unit, because it's an implicit account, and it's going to return an option with. And then here, none, fail with. So here, again, if it doesn't find the address, it's very unlikely because the address comes from a transaction that was sent to the contract, but you still have to handle it. And cannot find winner. In general, I try to have different error codes for each problem that can happen in the contract. So when you debug your contract or you debug your app, it's easier to find what the problem is. Then if we find it like that, and then here, okay, you will see the magic of it, like just like we did before. Transaction, so unit. We're going to send the whole balance that's in the contract. So again, we use the Tezos module. We have get balance with a parameter of type unit. So that's the amount in Tez that we're going to send to the winner. And then, of course, this value here. Now that's it. Here in the op variable, I'm going to have the operation that I'm going to send to the winner. That I'm going to send after the execution of the entry point to send the winnings to the winner. And so you can see it's true that at the beginning the syntax is not familiar, above all if you've never done any functional programming before. But it's a very powerful syntax, and it's very readable, and it's also a little bit better because you don't have to. Here you see that you know that it's a scope. It's a nested scope, so you know that everything that happens here inside is just going to happen in that little scope. It's not going to influence what's happening in the outer scope of the function. So even if you use the variables with the same name or things like that, it's not going to influence what's happening outside that scope. So Camel LIGO lets you, or Camel 2 lets you create those little scopes where you can do whatever you like inside, and it's not going to influence what's happening outside. So here we did different operations to get that new transaction that we're going to send, and it happened in that inner scope. And so now everything is ready, and we can send the operation. So you remember the value of type return. It's going to be a list of operations. So we have it here, and of course we have to update the storage now because we have to reset it to what it was at the beginning, so we can have new players coming and play again. So you remember that's going to be the storage like that with the with keyword, and then there are different properties that we want to update. So for example, players, we have to make sure that the players map is going to be empty for the new players to start playing again. So once again, use that map module, and there is an empty property in it that's just going to give you an empty map, and you have to type it explicitly just to tell the compiler that you want a map of this type. And of course, it has to be the same type like this one here, the players. And second one is going to be tickets available, because at the moment there are 0 tickets available, and that's where we're going to use max tickets. So we reset the number of tickets that's available to the maximum number of tickets that we want to give to the players. And so you see, in both cases, you have to return at the end of the execution a list of operation and the new storage. Now let's see if that compiles. Oh yeah, so it compiles the first time. So here you see the Mikkelsen. So when you see the Mikkelsen, it means that that everything is okay. Just to finish with this presentation and take some questions if you have, I just would like to show you quickly how to write views in LIGO. So there are an addition to contracts on Tezos that have been around for a few months now. But I see online a lot of questions about how do I set views, I mean on-chain views in my contract. And in LIGO, it's going to be very, very easy. So there is a decorator, like I don't know if they call it decorator or attribute, but okay, it's going to be the same thing. You just use this one. I think it's a decorator, and so the view decorator that you put like that just before you write the function. So a view, an on-chain view in LIGO is going to be a function. So for example, here, let's say I want to have a view with the and return the number of players that are already bought a ticket. Just like before, I named the function players member. I need to pass some arguments, and the arguments for a view is going to be a tuple. So the first argument is going to be the parameter that the contract that's calling the view is passing. So here we don't need any parameter because we're just going to return a number. So here we're going to have unit, and then the storage of the contract is also going to be on the right field of that tuple, so we can use it. And we also have to type it like that explicitly, and then it's going to return NAT. So the number of players that bought a ticket, and just like before, we're going to use that map.size and s.players. So map.size is going to return the size of the players map as a NAT. And here again, you see no curly braces, no semicolon. You just write, just after the equal sign, you start writing your code for the function. I think it should. And now you see it compiles, and here in the Michelson, you see the view that was added to the contract. So that's it for this contract. Let me close that. Okay. So I don't know if there are some questions about LIGO or about the contract. I think
Okay. Hi. I don't see any questions from the audience. Yeah. So I guess we can actually end the workshop here. If there's nothing else, so thank you so much, Mr. Crow. And yeah, I'll see you tomorrow. Yeah.
Yeah.
Okay.
So
Thank you.
tomorrow I'm going to explain how to write tests using also the LIGO language. So we're going to write tests for this contract.
Okay.
Oh, and maybe you wanted me to share the link to
the yes, the link, the GitHub link. So
yeah,
yes,
just give me a second to find it.
Yeah, you can type in a private chat here, then I can share it on the comments here as well. Yeah.
Yeah, I have it here.
Okay. Yeah.
So you also have sorry?
It's only for one link only, right? Yeah. Okay.
Yeah, there's just one link. So you also have contracts in SmartPy. So I worked with Anshu from Tezos India with that, and we worked together to have the same contract written in SmartPy and in LIGO. So you can compare the syntaxes, and you can compare how the contracts work. So you have a better idea about how everything works, and how different LIGO is from SmartPy.
Okay. Okay. Thank you, everybody. Yeah,
Okay.
we see you tomorrow. Yeah. Thank you, Mr. Crow again. Yeah. Okay. Have a nice day. Bye bye.
Okay. Thank you very much. Have a nice day. Bye.
Thank you. Bye bye.